Hi, everyone. In this talk, I'm going to talk about my work in a uniform decoupling inequality for polynomials. This problem was suggested by an advisor, Malabika Pramanik. We had very intensive discussion during the pandemic, and she really helped me a lot in formulating and proving the theorem. So the outline of the talk will be divided into 4 steps. First, we talk about the backgrounds of decoupling, and then we talk about why decoupling works, in particular, the heart of the matter, the curvature of the curve of the decoupling. And then we're going to talk about my main result, and lastly, the idea for the proof of the main result. First of all, what is L2 decoupling? In principle, this can be defined in a very general way as follows. Let script A be a finite collection of disjoint measurable subsets of R to the n. Most typically, there will be open sets being the neighborhoods of some smooth manifold. For P, for Lebesgue exponent P, let this D sub P of script A be the best constant such that for any functions fi with Fourier supports in each of the sets ai, we have the following inequality. So on the left-hand side, you have the sum of the functions evaluated in the LP norm. And on the right-hand side, you have the little L2 sum of the capital LP norm of the functions fi. And this is why we call this a little L2 decoupling inequality. And our goal is to find the best estimate for this decoupling constant, d sub p of a. Let us first check some very trivial estimates of this decoupling constant. First of all, of course, the decoupling constant is bounded below by 1 because as we know, the decoupling inequalities would hold for an arbitrary collection of fi. So no matter what fi you choose, this decoupling has to work for that fi. So in particular, we could choose one fi to be non-zero and all the other fi's to be 0. In this case, we get the trivial bound. And on the other hand, if we don't know the information of fi's at all, we can still always bound the left-hand side by the triangle inequality of the LP norm first, and then apply a Cauchy-Schwarz inequality. The result is that the decoupling constant is always bounded about by 1/2 of the cardinality of the script A. And another very important observation is that when P is equal to 2, actually this is equal to 1. And this is very easily seen by the Plancherel's inequality, because if P is equal to 2, you could just transform the left-hand side to be its Fourier transform, and using the fact that the Fourier supports are disjoint. This is also a very important assumption. So actually, there's also a very simple argument which shows that L2 decoupling is trivial for P less than or equal to 2, but for this time being, we will not be talking about that. And most people are just interested in P bigger than 2 because this is the non-trivial part of the decoupling estimates. First, so now we are in the case that P is between 2 and infinity. First, we talk about a special case which we call flat decoupling. What does that mean? So before, we didn't have any assumption on the sets A, on the sets AI. So for different choice of this family of sets AI, we would expect to have different estimates of the decoupling constant. For example, suppose now A is defined by cutting a rectangle in R to the n into n equal pieces. So you let AI to be like A1, A2, up to A10, for example, in this case, to be consecutive smaller rectangles. In this case, you could use some very trivial test functions, fi to be taken to be the characteristic function of each of the AIs. So after that, you could get a lower bound up to some constant, which is roughly equal to the cardinality of I raised to this power. I will not be talking about how we get the estimate in this talk. And on the other hand, we could do interpolation between p and 2 and p equals to infinity. Recall that for p equals to 2, we were actually using the Planck-Ross inequality, and for p equals to infinity, this trivial triangle inequality and Cauchy-Schwarz is what we use. So by interpolating these two bounds, we are able to get an upper bound of this form. And notice that up to a constant, this upper bound is the same as this lower bound. So in this case, this tells us that flat decoupling is also very trivial, because we've got a sharp upper bound and a lower bound if this set A is formed by by the partitioning of a flat rectangle. So what does this suggest? This suggests that to get some non-trivial decoupling, we need the geometric figure to be non-flat. So a first example is the classical example proved by Bourgain and Demeter. So what they considered is a curve, and the model case is just the unit parabola. For example, phi of s equals to s squared. We divide its vertical delta neighborhood into these pieces, and each of them has width delta to the power 1/2. You may ask why we choose this scale. So later I will explain why this is important when we come to the geometry of the problem. But before that, let's first talk about what they have managed to prove. So if each a of I is defined to be the delta neighborhood of the graph over this interval, so like the one we saw before. So in this case, for example, this one is A1, A2, A3, etc. And they are curved, which is very important. In this case, they have managed to show that the decoupling constant with respect to this set, script A, is bounded about by delta to the power minus epsilon for every epsilon positive. So this will be frequently referred to as epsilon loss in the estimate, and this is actually a very common feature. This is slightly worse than saying that the decoupling constant is bounded about by a constant, but this is again very strong, because this epsilon could be taken to be arbitrary. And what we expect is that when this epsilon goes to 0, the constant, depending on epsilon, will be going to infinity. So if we could still ignore the epsilon loss here, then we could even say that the decoupling constant is roughly 1, like a very rough equivalence here. And what I should mention again is that this theorem only holds for p between 2 and 6. So p cannot go up to infinity. This is observed by a very simple exponential sum estimate, which I will not be talking about today, but it's very useful. And then the key why this theorem holds is, of course, the curve phi has non-zero curvature. So we could actually do a simple computation. So for we know that for a given function phi, the curvature is actually defined by phi double prime over over this expression to the power 3/2. And we know that here the denominator is roughly 1 because phi is defined on a bounded set. And in this case, the numerator is roughly equal to 2, or which is roughly equal to 1. And in this case, we know that this is positive. And the proof technique suggests that the theorem, Bouguerin-Demeter's theorem, holds not only just for the function phi of s equals to s squared, but for every function such that the infimum of phi double prime is positive. So this means phi double prime never vanished, or this means that the function phi defines a curve with non-zero curvature. So the rough idea for the proof is to use an induction of scales argument. We use the d script p of delta to denote this script of script a, because now this script a is dependent on the scale delta you chose. We first show a bootstrap inequality roughly of the form this. So each time we go from delta to the power 1/2, and it's not difficult to see that after iterating this inequality for log delta inverse many times, we would iterate from the scale delta to roughly a constant, like 1/4. And because each time there's a constant here emerging, and lastly, we should raise this constant to the power log delta inverse. So after that, you would get roughly log delta inverse, which is still bounded about by delta to the power minus epsilon. So we are done. Okay, so now before we talk, after we talk about the classical theorem, now I want to talk about the monic cubic function, which is the more non-trivial problem that I considered as a model case. First of all, if we compute the derivative, the double derivative of phi, we see that the double derivative of phi evaluated at 0 is actually 0. So this means that this condition, like the infimum of phi double prime is bigger than 0, is not satisfied. And in this case, a Bouguerin-Demeter, their classical theorem does not hold. So what do we want to do? First, let's show a picture of this, the vertical delta neighborhood of the function. So what we did is that if we chose our script A suitably, then we could still show that the decoupling constant is bounded about by 1 up to an epsilon loss. And also P is between 2 and 6. But in this case, we notice that the width are actually changing. And what we can see is that as S gets larger, the width is decreasing. Why is this the case? This is because as x gets larger, the curvature of the function phi becomes larger. And why is it the case that for smaller curvature, we need to we need to enlarge the length? We shall see this in a moment. Okay, so now we talk about the geometry, the curvature. And here we talk about the key geometric observation that makes us makes the choice of the length of the intervals. Okay, so for example, if we go back to the case of this unit parabola, we knew that the length we chose was uniform. But why is that the case? Because the geometric observation is that on each of this of such a vertical neighborhood, this is roughly equal to a rectangle. By roughly equal, I mean you could find a rectangle contained in this vertical neighborhood, and at the same time, a constant dilate of the rectangle would contain the curved neighborhood. So it's very important that this constant is uniform. So this constant only depends on the function phi you chose, but it cannot depend on the delta. So this delta 1/2 is actually the largest scale so that this would hold. Does this mean? So to be more precise, for each different phi you are given, and for each different scale delta you are given, which can be very small, you would need to choose the coarsest partition. So in this case, each of the intervals would have the largest length in the x-axis. So you choose the coarsest partition so that for each interval inside this partition, the delta neighborhood of the graph above I is a normal rectangle in a sense we described before. And why should we do that? Because as we saw just now here, we know that flat decoupling is trivial. And this constant is, of course, not 1 if P is not 2. To avoid this flat decoupling to happen, these neighborhoods cannot have a flat part. And this forces you to choose the coarsest scale. Because if you chose a finer scale, then I could, if I decouple this part will give you an estimate of the flat decoupling. So that's why we have to make it the coarsest partition. And yeah, so this is the geometric observation of how we choose the partition, and correspondingly, there's an algebraic version. So here, the translation of this almost rectangle into Taylor expansion is of this form. So this gives us a criterion for us to check whether one interval I is almost rectangle or not. Okay, so for example, we can plug this in actually. For example, let's see when phi of s is equal to s squared, we knew that phi double prime is roughly a constant, and this would imply that I is roughly equal to delta 1/2, which we expected. And on the other hand, if phi of s is equal to the Monega cubic, then phi double prime of s is roughly equal to s. And in this case, what we have is the interval I would have length roughly equal to s to the power minus 1/2 times delta to the power minus 1/2. And we could easily check that in this case, this is true. Because in this case, what is s? S is roughly j to the power 2/3 delta 1/3. And then what is I? I is roughly j to the power negative 1/3 delta 1 over 6 times delta to the power 1 over 2, which is this. And as we see, but as we see from here, what is I? I is roughly j to the power negative 1 over 3 times delta to the power negative delta to the power 2 over 3. And this is easily seen by, let's say, the mean value theorem. So we see that these two scales actually, they are equivalent. So this is why we chose this scale as the admissible partition. So we can also see that when j is increasing, this number becomes smaller and smaller, and the whole scale becomes smaller and smaller. Okay, so but we have already talked about a special case of my theorem in here, but now let's talk about the main theorem in full generality. Recall our title where I said that I proved a uniform decoupling inequality. So now let's see what it says. For any p in this range, for any degree, so this d is the degree of the polynomial, and epsilon positive, there's a constant c epsilon depending only on this 3 parameters, such that the following holds. For any delta small, for any polynomial of degree at most d, with coefficients bounded by 1, this is not very important. So we can ignore this at this moment. And any admissible partition P of 0 and 1 for phi at a scale delta. Yeah, I haven't defined what it means by admissible partition, but the formal definition will be given later. And actually, we have already seen for the case phi equals to s to the power 3. So in this case, we have seen what it roughly means by an admissible partition. So given this partition, we would have the following decoupling inequality for every f supported, Fourier supported on the neighborhood of the graph of phi. And this part is standard. So what is special about this theorem is that this is a uniform decoupling inequality. And what that means is that this C epsilon depends only on the degree of the family of polynomials on P and epsilon. So this C epsilon would work for any polynomial of degree at most D and any partition P as long as it's admissible in this geometric scale we talked about just now. So this generalizes a theorem of Biswas and many other authors. Okay, so yeah, so what is actually so this admissible partitions is actually like in this sense we talked about just now, and for a more rigorous definition of an admissible partition, you could refer to my archive uploaded version. There will be a formal definition of it, but for this talk, I will not be. I will omit this for the moment. So lastly, we talk about the main idea for the proof in a very brief way. First, because we want to prove a decoupling inequality, we first let this dp d of delta to be the best constant, so that under the assumptions of the theorem 3, we have this inequality. So we call that this d is the degree and p is the Lebesgue exponent, and we need to show this inequality. And the key is to prove a bootstrap inequality of this form. For p in this range, epsilon and d be given. For any large intermediate scale m to be determined, we need to show that there's a constant C such that for each delta we have the following. So we can bound the required decoupling constant by two terms. The first term is obtained by considering the part where phi double prime is bounded below by M inverse. So M is an intermediate scale, and in this case, phi double prime is bounded below. So we can use Bogan and Demeter to conclude the proof. And now, of course, this constant C has to depend on the intermediate scale M. And what about the second term? The second term is when this phi double prime is very small. For example, this is the case when s is very close to 0, in the case phi of s equals to s to the power 3. So, but in this case, because we are dealing with a polynomial, we could actually apply a polynomial rescaling argument, which is similar to the parabolic rescaling in Bogan and Demeter. So the result is that for this part, you can bound the decoupling constant by this one, which roughly says that you could upgrade from the scale delta to the scale m delta. So each time you multiply the scale by m. So after some time, you would get to roughly a constant power. And if we are able to prove this inequality, we could iterate this. So we could iterate this for roughly log delta inverse many times until we get this bound for the decoupling constant. And this standard inductional scales is the same technique that Bogan and Demeter used in their original proof. Yeah, I guess that's the end of my talk. Thank you for coming.